going to talk about units of measurement. Units are really important. This is going to be abbreviated. So there's two main systems, the metric and the English. We don't use the English system in chemistry. So when I ask you to measure the length of something, I want it in centimeters, not in inches. The metric system and the international system of units are essentially the same. The differences are dumb. So I consider them essentially the same. You know, just talk about that. A meter is similar in length to a yard. It's a good idea to have an idea of how big these metric units are. So a meter and a yard, they're not exactly the same. But here we have pictures, they're about the same. Mass is the quantity of matter. It's not the same as weight. Weight is a force. It's the measure of gravitational pull. So your weight changes depending on what planet you're on, or if you're on the moon or something. Anybody planning to leave the planet this semester? Yeah, I didn't think so. So as long as you stay on the planet, we can kind of use weight and mass interchangeably, but they are different. Mass is quantity of matter. It does not change depending on where you are in the solar system. Kilogram and gram are common units of mass in the metric system. A kilogram is a little over 2 pounds, and a gram is 1/1000th of that. So grams, very small amount of mass. Second is a unit of time. It's the same as what we use, hours, minutes, seconds. Temperature, in some situations we use the Kelvin. And we're going to talk about temperature units later. And this I've kind of already mentioned. Temperature is a measure of kinetic energy of the particles. And temperature determines the direction of thermal energy transfer. It always moves from the hot object to the cold object. Hot object has more energy. The energy flows to the cold object with less energy. So here we'll talk about the temperature scales. Here we have 3 thermometers side by side. The Fahrenheit is what we use in everyday life. What the weatherman tells us it's going to be 95, he means degrees Fahrenheit. Boiling point of water is 212. Freezing point of water is 32 degrees Fahrenheit. Kind of random numbers, like many of the numbers in the English system, they're random. In this span, there's 180 degrees. The Celsius scale was designed to work better with the metric system, and so they established 0 as the temperature of water freezing and 100 as the temperature at which water boils. So there's 100 degrees of difference. So a Celsius degree is larger than a Fahrenheit degree, and they are also offset because they don't start at the same point. The Kelvin scale is something we use when we talk about gases, and it's based on the idea of absolute zero, which is the temperature at which all motion would stop. So you take a solid and you cool it down, the particles move slower and slower until they do not move at all. And that would be 0 Kelvin. They've gotten really close to it. Nobody's actually attained 0 Kelvin yet. So on the Kelvin scale, water freezes at 273 and boils at 373. Again, this is a difference of 100 units. So a Kelvin and a Celsius degree are the same size. They are just offset, because here 0 is equivalent to minus 273. Absolute 0 is the lowest possible temperature. There's nothing that could be colder than that. Okay, I said all that. Here's the formulas. So you need to know how to convert between Celsius and Fahrenheit and Celsius and Kelvin. So you should memorize these equations and know how to use them. This one is set up for finding the Celsius temperature if you're given the Fahrenheit temperature. If you're given Celsius, you would have to rearrange the equation. The Kelvin to Celsius equation is much simpler. It's because the size of the degree is the same. They're just offset by 273. So let's do an example. Mercury melts at 234 Kelvin, lower than any other pure metal. What's its melting point in Celsius and Fahrenheit? So we've got 234 Kelvin. So what's the relationship? Now let's back this up. What are those two equations? Close. Kelvin is Celsius. Oh, I'm blanking. I'm blanking out. Plus 273. So the Kelvin temperature is the Celsius temperature plus 273. So if we're given the Kelvin, we need to take this equation and we need to solve it for degrees Celsius. So to do that, we would subtract 273 from both sides. We would come up that the Celsius temperature is the Kelvin temperature minus. So if we put the 234 in there and subtract 273, we're going to get minus 39.15 degrees Celsius. So that's a pretty cold temperature. When we're doing problems, it's a good idea to show your work. Write down the equation. So like I did here, I wrote down the equation I was starting with. Sometimes there might be multiple steps in rearranging the equation. It's best to write all those out. Other times, like with this one, we can kind of rearrange it in our heads. If you're having trouble rearranging equations, please come and talk to me because I can help you with that. But here I wrote the rearranged equation. I wrote that equation with the number put in, and then write the answer with the unit. Units in temperature conversions are kind of weird because they don't cancel out like they do in other conversions. So you just kind of have to know what unit to slap on it at the end. Let's see, that was, the other temperature one was Fahrenheit minus 32 over 1.8. Is that right? I don't remember if there was a zero there or not. It doesn't really matter. Now, this equation is great if we know the Fahrenheit temperature, but if we know the Celsius and want to calculate the Fahrenheit, we need to mess around with it a little bit. Sometimes students want to put the numbers in and then rearrange the equation. I don't recommend that. It causes all kinds of trouble. So I'm going to model not doing that. Let's rearrange this equation first. Some of you might be a little bit rusty on your, equation rearranging. What we're trying to do is we're trying to get Fahrenheit by itself. So we need to get rid of the minus 32 and we need to get rid of the 1.8. To get rid of the 1.8, we're going to do the opposite. So it's divided by 1.8. If we multiply by 1.8, then we have 1.8 divided by 1.8. That's 1. We can cancel that out. But if we do that on one side, we have to do it on the other side as well. So I didn't leave much room over here. So 1.8 times the Celsius temperature. Now we have, I'll just write this out again. 1.8 times the Celsius temperature is equal to the Fahrenheit temperature minus 32. To get rid of this 32, we need to do the opposite. So we're subtracting 32. If we add 32, what's minus 32 plus 32? It's 0, right? So poof, those go away. If we add 32 to one side, we have to add 32 to the other side. A mathematical equation is like a teeter-totter or a balanced beam. If you do something to one side, you have to do the same thing to the other side in order for it to stay equal. So there, rearrange the equation. So the Fahrenheit temperature is 1.8. I'll throw that 0 back in there. Doesn't really matter though. Times the Celsius temperature plus 32. So now I'm going to plug my number in that I got, which was minus 39.15 plus 32. And then use the calculator. Sometimes you can do these things in your head, but then it's good to check your math on your calculator. So I'm coming up with minus 38.47 degrees Fahrenheit. Anybody else get that? Okay. When you're doing calculations on your calculator, it's very easy to make a mistake, isn't it? Sometimes you push the button, but you didn't push it hard enough, and it didn't register. Or it does it twice, or you just did something dumb. So what I recommend is always run it through twice. If you get the same answer, you're either really good at making mistakes consistently, or you did it correctly. If you get 2 different answers, go for best 2 out of 3. Okay? Because it's silly to do all the work and have the right idea and understand it, and then get the answer wrong because you miscommunicated with your calculator. Any questions about this? This should be a review. The metric system uses prefix multipliers. There is an appendix in your textbook. I'm going to assume that you understand scientific notation. If you are rusty on that, go to the appendix and read through that. In Mastering Chemistry, there's also some math review sections in the study area, and I recommend working through those if you're rusty on your math. The metric system uses prefix multipliers to change the size of the unit. In the English system, they just use a different unit. Inches and feet measure length, but they have completely different names, and the relationship between them is strange. A foot is 12 inches, and the next increment up is a yard. A yard is 3 feet. A mile is 5,280 feet. That's a random number, isn't it? In the metric system, everything is based on powers of 10. So you have one base unit, the meter for length, but sometimes we need it to be bigger or smaller. You don't want to measure the distance between Reedley and Fresno in meters. It's going to be big. You don't want to measure the distance between the Earth and the Sun in meters. You don't want to measure the diameter of a human hair in meters. It's way too big. We want the size of the unit to be comparable to the distance we're measuring. So we make the unit bigger or smaller. We have kilometers and millimeters and micrometers. We just make the unit a different size. And that works with all the metric units. So the multipliers change the value of the unit by powers of 10, just like scientific notation does. So the kilometer has this prefix, kilo. I just slap it on the beginning. Kilo means 1,000. So 1 kilometer is 1,000 meters. Instead of writing the number 1,000, we write lowercase k. It's like a nickname or an abbreviation for 1,000. So 1,000 meters is the same as a kilometer. So here are the metric prefixes. There's a bunch of them, and I think there's some that are not even listed here. Oops. Kilo is important. Mega, centi, milli, micro, nano. Those are the ones that we will use the most. You definitely should memorize those. They're abbreviations. Mega makes something bigger. You know, that movie star makes mega bucks. Mega literally means 1,000,000. So its meaning is over here. It's 10 to the 6th, or 1,000,000. We look at this number, 1,000,000. How many zeros are behind it? 6. That's 10 to the 6th power. This number has 9 zeros, so that's 10 to the 9th. So this exponent has to do with moving the decimal point around, has to do with the number of zeros. Here 1,000 is 10 to the 3rd. Personally, I think it's easier to remember the meaning of these multipliers as 10 to the power of something. Most of the ones we use frequently are multiples of 3. So mega is 10 to the 6th, kilo is 10 to the 3rd, centi is weird, centi's 10 to the minus 2, it's 1/100th. There are 100 pennies, 100 cents in a dollar, 100 years in a century. Cent has to do with 100. Then there's milli, 10 to the minus 3, micro, 10 to the minus 6, and nano, 10 to the minus 9. Nano is easy to remember because nano and 9 are kind of similar. So mega makes it bigger. Mega has the abbreviation or the symbol capital M. So we've got 3 M's going on here. We've got mega, milli, and micro. So mega is a capital M because it makes it bigger. Milli is a lowercase m, makes it smaller. And we ran out of English M's, so we went to a Greek lowercase m, which is the micro, which is like a U with a funny tail on the front, or a backwards Y. Kilo is a lowercase k, centi is a lowercase c, nano is a lowercase n. So we need to know what those mean. So if we see a number like this, 4.5 capital M, M. The capital M is significant. And when you make a capital M, you make it bigger than the small m. Because capital M and lowercase m mean different things. So what does the capital M stand for? Mega stands for mega. So this is a megameter. So if we were going to write this out in terms of meters, this would be 4.5, and mega means what? 10 to the 6th times 10 to the 6th meters. A megameter is 10 to the 6th meters. Let's look at this number. This is a small number because it has a negative exponent. 7.13 times 10 to the minus 9th liters. So just a quick, well, no, I'm not going to go there. Save my voice. So what prefix means 10 to the minus 9? So that's a nanoliter. There's a problem with this question, isn't there? Good grief. Better fix that. It was supposed to be nanoliters, not picometers. You can't convert liters to meters. It doesn't work. So we can convert this into nanoliters because 10 to the minus 9 means nano. They're the same thing. It's like nicknames. My third son is named Thomas. But we don't call him Thomas. We call him Tommy. Are Thomas and Tommy different people? No. Different names for the same thing. N and 10 to the minus 9 are different names for the same thing. It just means that we're taking liter, which is a large volume, think half of a 2-liter soda, and we're making it smaller. We're saying divide that by 1 billion, and that's a nanoliter, teeny tiny amount. So this amount is 7.13 nanoliters. Any questions? We'll do a little more with the metric system in a bit here. So we talked about length and mass and time as quantities that are measured. We also have some derived quantities or derived units. And a derived unit is one that's a combination of other units. So for speed, we have miles per hour or meters per second. It involves a length unit and a time unit. So volume is a measure of space. If we take a unit of length and cube it, it becomes a volume unit. There's probably a better picture on the next page, but oh well. So if this is 1 meter on each side, then the volume of it, volume of a cube, is length times width times height. So that's going to end up being 1 meter cubed. We take a length, we cube it, and that gives us a volume unit. And that can work with anything. So we can have cubic meters, cubic millimeters, cubic centimeters. You can also do it with English units. In the metric system, we also have a unit of volume called a liter. A liter and a milliliter. Milliliter, what does milli mean? Do you remember? Milli's 10 to the minus 3. So this is 10 to the minus 3 liters. Is that bigger or smaller than a liter? It's smaller. So we can use cubed length units to measure volume, and we can also use liters and milliliters, picoliters, any other combination. It's a little bit like in the kitchen you measure volume of liquids sometimes in ounces, right? There's fluid ounces, which is not the same as a mass ounce. Maybe you didn't know that. So relationship between length and volume. So here's a cube. It's 10 centimeters on a side. So that means that there are 1,000 cubes, right? Because 10 times 10 times 10 is 1,000. So there's 1,000 cubes in there. If each of these cubes, if there's 10 on a side and it's 10 centimeters, then each of these is 1 centimeter, right? So there's 1,000 of those. This centimeter here, this cube is a centimeter on a side. It has a volume of 1 cubic centimeter. Oops. So this guy over here, volume, 1 cubic centimeter. That is given a special name. It's called a milliliter. So a milliliter is the same as a cubic centimeter. In medicine, They call it a cc for cubic centimeter. So I just put a 1 there. 1 cubic centimeter, 1 milliliter, 1 cc, they are all the same volume. Usually when we have a liquid, though, we're going to use milliliters. If we're measuring a solid, we tend to use something like cubic centimeters. It doesn't have to work that way, but usually. So in this big cube, there are 1,000 of these cubic centimeters. So that means that has a volume of 1,000 milliliters. Milli means 10 to the minus 3 liters. What if we have 1,000 times 10 to the minus 3? What does that equal? 1. 10 to the minus 3 is 1 over 10 to the 3, or 1 over 1,000. Oops, got carried away. So 1,000 milliliters is 1 liter. So this big cube is a liter. It's 1,000 of the smaller cubes, and this one is a milliliter. Here are some common units and their equivalents. This table is in your book. This is important, so I pulled it out there. Note, a cubic centimeter is the same as a milliliter. That's something students forget a lot. You're doing some conversion problem and you hit a wall. It's because you're missing this little guy right here. You should memorize this one. An inch is 2.54 centimeters. This, notice it says exact. We're going to talk about significant figures and exact measurements. What they did was they redefined the inch to be exactly 2.54 centimeters. It just made everything simpler. So you should memorize that one. The other ones, if you needed them on an exam, I would give them to you somewhere. What I expect you to be able to do is convert units within the metric system, like milliliters to kiloliters or something like that. You need to be able to convert between metric and English, but there are so many different relationships, and the numbers are so weird. I don't think it's worth taking up space in your brain to remember those. The exception is this one because we end up using it a lot. But the rest of these, know where to find them, know how to use them. So that's volume. Another derived unit is density. Here's the density equation. Density is the ratio of mass to volume, or just with letters, D equals M over V. There's a joke, which weighs more, a pound of feathers or a pound of bricks? They weigh the same, right? They weigh a pound. Which one takes up more space? The feathers. Because the feathers are less dense. Feathers are light and fluffy. Bricks, we say they were heavy. They're dense. They have a lot of mass in a small amount of volume. Feathers take up a lot more space for the same amount of mass. It's the relationship of mass to volume. So you can have a small object that is more dense than a large object because it's the ratio of mass to volume. That's a concept that is hard for some people to get, so you need to work on that maybe. Common units for liquids and solids are grams per milliliter. There's a unit of mass divided by a unit of volume, and grams per cubic centimeter. Again, mass divided by volume. The density is a physical property of a substance. It does depend on the temperature. When you heat something or cool it down, the density of it will change. Some things change quite a bit, others not so much, but it does depend on temperature. So let's do an example using density in a calculation. A piece of galena, which is an ore of lead, has a volume of 4.6 cubic centimeters. If the density of galena is 7.5 grams per cubic centimeter, what is the mass of that piece of galena? Well, it's always a good idea to identify the numbers that have been given to you in a question. Chemistry has a lot of word problems in it. And I know that there are a lot of people in chemistry who hate word problems with a passion. And you have my sympathy. I'm not one of you, but you have my sympathy. And I will do my best to make them as friendly as possible. The numbers are always important. So pull these numbers out. 4.6 cubic centimeters and 7.5. Now this is written as a horizontal fraction because that's a lot easier to type. But when you're showing your work, when you're writing with your hand, make it into a vertical fraction because that makes it more obvious that this is a fraction. So grams per cubic centimeter. A volume of this. So they're telling us that that's the volume. So let's label it. If they didn't tell us that, we should be able to look at the unit, cubic centimeter, and say, oh, that must be a volume. This is the density, we'll call it D, and we should be able to identify that also from its units. Grams per cubic centimeter, those are density units. And what are they asking us for? The mass. Mass equals question mark. Many problems have multiple ways that they can be solved. Since we just talked about that density equation, we're going to use the density equation to solve this one. We know that density is the mass divided by the volume. Here we're given the volume and we're given the density. We need to find the mass. So we take the equation and we rearrange it. So we're going to multiply by V so that the V's cancel out. And if we do that on one side, we have to do it on the other side. Now over here we have mass left, and that's what we wanted to do. So mass is volume times density. So the volume is 4.6 cubic centimeters. And we're going to multiply by the density of 7.5 grams per cubic centimeter. The calculator, 4.6 times 7.5. 34.5. Always write your units in your equations and then look at them and see what happens to them. Units can be treated like variables in algebra and you can cancel them out. Centimeters cubed divided by centimeters cubed is 1 because anything divided by itself is 1. So these cancel out and we're left with the unit of gram. So we're going to put that there. Units are really, really, really important. The NASA lost, I think it was $125 million orbiter because the scientists working on it didn't communicate about the units they were using. One team was using metric units and one was using English units. So basically it came down to centimeters and inches. And the calculation was off. And so the orbit was wrong and it crashed. $125 million. It's in your textbook. Maybe it was $1 billion. I don't know. It was just crazy. Units are really, really, really important. I know it's tedious to write the units all the time, but it's also tedious to take the class over again because you failed. And when you don't write the units, you are much more likely to get the wrong answer. Okay, so always, always show your units. So there's our answer right there. A little bit more about properties, intensive versus extensive. Intensive properties do not depend on the amount of substance. It's more like an intrinsic thing. It doesn't matter how large the size of matter is, it has that property. And we can use intensive properties to identify substances. So density. The density of a substance doesn't depend on how big it is. Because if you cut the mass in half, you're going to cut the volume in half too, and the density will be the same. The melting point of something doesn't change with its size. If you are melting an ice cube or an iceberg, it's still going to melt at 0 degrees Celsius. The color of something doesn't change depending on how big it is. Those are intensive properties. Extensive properties depend on how much substance there is. So these are things like mass, length, and volume. The length of something is going to depend on how much there is. It's an extensive property. You can't identify a piece of copper based on how long it is. One of my nephews, who is, he's going to turn out to be a brilliant physicist, but he was rather clueless as a young child. And I think he was in middle school, and he wanted to walk to his friend's house in the neighborhood, and his mom was like, not real sure if he really knew where he was going. Well, how do you know, tell me how you're going to get to this person's house. How are you going to find his house? Well, that's easy. It's the house with the yellow car parked in front. What's wrong with using that as an identification for your friend's house? Car might not always be there, right? They may have gone to work. They could have sold the car. It just doesn't make any sense. We can't identify things based on extensive properties because those can change even though the matter itself is not changing. It's still copper metal even if you cut it in half. The density is an intensive property. The melting point, the color, those do not depend on size.